Message you.
Okay. Hello everyone. Welcome to Horizons Summer School.
I am Rajiv,
And I'm Akshay.
and we are presenting to you Fusion and Fission, Stars, Oppenheimer, and Clean Energy.
So, let me tell you something which may blow your minds. All the energy that you have used until now and you will use in your entire life is from nuclear reactions. Well, if you don't believe me, that's actually quite a valid reaction. But let me elaborate. So, first, I hope you'll agree with the following statement. Nearly all the energy that you will ever use has come from the sun. Or unless you're in the rare places like France or Himachal Pradesh, where energy is from geothermal or nuclear reactors, the sun is the only source of energy for you. Now, the sun itself is going to run on nuclear fusion because every single bit of energy coming from the sun is powered by the fusion of hydrogen atoms to helium atoms in its core. And therefore, ultimately, the sun is the overall source of energy. But you may ask, what if we burn wood? Well, you have a very valid point, but nonetheless, you must ask yourself the question, where did this wood get its energy from? Well, again, the answer is very straightforward. We should look at where it was initially. So, wood is basically just dead plant matter. And where do the plants get their energy from? Well, they get their energy via photosynthesis, which in turn is powered by the sun. So, indirectly, when you're burning wood, you're effectively using stored solar energy. You may say, okay, fair enough, but what about coal or even petroleum? Coal is basically wood, but millions of years old, and it has gone through the process of fossilization. And then, therefore, indirectly, coal is also effectively stored solar energy. Now, moving on to petroleum. Well, there are, of course, oil rigs in the middle of the ocean drilling out petroleum. But then, petroleum is not just a liquid as it was today. But rather, once upon a time, these were basically animals, and animals get their energy indirectly from the sun. How? Via the food chain. So now, when you think about it, all the energy, even in the form of fossil fuels, is basically from the sun. Now you may say, what about clean energy sources? For instance, what about wind energy? What about the windmills which are running? Well, ask yourself this: what exactly is going on here? The wind is basically pushing the turbine blades to rotate and generate electricity. But then, what exactly is causing these winds to flow? The answer is straightforward: pressure differences in the atmosphere. But then, what causes these pressure differences in the atmosphere? We must look further and we realize that these pressure differences arise due to temperature differences in various parts of the earth. So, now let us look at the simplified example of sea breeze and land breeze here. Basically, what happens is that water and land get heated up and cooled down at different rates, which means there will be differences in pressure as well. So there will be winds established depending upon what part of the day it is. Then, of course, there is all obviously the other form of clean energy, solar. But then my point still stands. Solar energy is directly from the sun itself. But yes, this is another clean form of energy. Of course, we do have hydroelectric power as well. But then hydroelectric power is basically you extracting electricity by rotating turbines which are present under dams, which in turn are powered by falling water. Now, where does the water get its energy from? The answer is straightforward: gravitational potential energy, or basically, since the water is stored higher, it has a tendency to fall down. And this in turn becomes kinetic energy, and this in turn becomes electricity. But then, after a certain point of time, after a large period of time, if you want, pretty much all the water will go to the lowest possible place it can. But then, what really carries it up back to the original point near the dam? Well, the answer is the sun as well. When you think about it, the hydrosphere, the hydrosphere is continuously a cycle where water is moving downhill all the time, but then go to the fact that the water keeps coming uphill because of the sun's energy, because solar radiation will evaporate the water, and then this will precipitate back to the earth. And then this water cycle is what enables us to harvest energy. So, when you think about it, nuclear energy is essential to life. And pretty much all the energy you will ever use is from nuclear reactions. It only makes sense for us to study the basics of nuclear reactions before we try to understand what exactly is going on behind the scenes. So, before we actually dive into the topic, I invite you to perform this thought experiment with me. So, suppose I give you a set of spheres, and these spheres are all coated in super glue, a very strong super glue for that matter. And assume that half of them are magnetic and the other half are made of wood. Now, these magnetic spheres, these aren't your typical magnets, because the magnets which you see every day have a north pole and a south pole. But these magnets, assume that they are only the north pole. Through some unknown mechanism, this is possible. So now, hypothetically speaking, if I want to build something, I would bring multiple spheres of these together. But when you think about it, if I want to bring multiple magnets close together, it will be a bit of a challenge because of the magnetic repulsion. However, once they're attached, the super glue holds it together, and it is pretty much impossible to break the super glue. So that is pretty much what happens. But then, if you do want to build larger and larger and larger structures, you will want to put some more distance between the magnets to decrease the repulsion. So what do? You put something else in between. And in this case, the wooden balls. So the wooden balls also have super glue, which means they can still hold everything together, and they can also provide the structural support. But also, they don't really contribute to the repulsion directly. So it is possible for us to build large structures with the help of these magnets and wooden balls. However, there will always be a limit to this, because after one point of time, even the superglue won't be able to counter the overall magnetic repulsion. Once you put a lot of these magnets, maybe hundreds, the magnets will have the capability to even push back the superglue and even break the superglue. And this is also possible. Of course, having wooden balls prevents this by a large margin, but nonetheless, it is possible. And you may ask, what is the point of this thought experiment? Well, because frankly speaking, this is essentially what happens even at the nuclear level. So these terms I was using were basically metaphors. We don't have magnetic balls. Instead, we have charged protons, which are positively charged particles. We don't have wooden balls. Instead, we have neutrons. And these clumps of matter are called nuclei. Now, there's one more point which is to be noted. Suppose I pile up a lot of these magnets and wooden balls together. But then there will be a point after which I will put a lot of energy towards getting these things to attach, that the energy which is released by the super glue will be less than the energy I have put in to attach these magnets together. And this is actually observed in real life as well. We can experimentally detect this. What this indicates is that there is a sweet spot between magnetic repulsion and the glue's attraction, at which the most stable configuration of these magnets and wooden balls exist. This particular stable configuration can be determined experimentally. And the same is true even in the case of actual atomic nuclei. It turns out that this particular stable element has the most stable nucleus. And if I ask you to guess, you might say something like neon or argon or some other noble gas. However, the element that I'm referring to is actually not a noble gas because I'm not discussing the chemical stability of the atom here, but rather I'm discussing the stability of its nucleus, which is totally different. The element which is the most stable turns out to be iron. Now, again, to analyze all these interactions more easily, scientists have figured out a way to quantify it. So, as I said, there will be some energy spent in bringing these balls together, but every time the super glue gets solidified, it releases some energy. Similarly, we can observe what happens at subatomic level. So, what happens here is that the superglue, which I've been referring to, has a counterpart at the subatomic level. It is something called as the strong nuclear interaction, and this releases energy. So, overall, we can experimentally determine how much energy is released and how much energy has been consumed during the creation of said nucleus from its constituents. And this quantity of the overall energy released is called binding energy. And this binding energy is very fundamental to measuring the stability of a nucleus. Now, the binding energy itself directly is not very helpful because when you think about it, a much larger atom will most definitely have a higher binding energy than a smaller atom. So instead, we take the ratio of the binding energy to the number of particles present in the nucleus. And protons and neutrons together are termed as nucleons because they make up the nucleus. So the quantity in question is called binding energy per nucleon. The higher the binding energy per nucleon, the more stable it is. So what we can conclude here is that all nuclei try to have the highest binding energy per nucleon, which is the conclusion for this. So overall, what we can infer is that all nuclear reactions aim to increase the overall stability of the nuclei, and iron is the most stable nucleus. Now, of course, we have to look at some of the nuclear reactors present, and the most common nuclear reactors are ones which are made by nature. And nature's most common nuclear reactors happen to be fusion reactors. So let us go on and have a look at them.
Yeah. So the sun and all other stars shine because of the energy released by nuclear fusion. These are nature's most abundant nuclear reactors. Now, just by looking at the night sky, we may say that they all look similar and must be pretty much the same. However, all the stars are vastly different. And what define these differences in the star are its mass and its age. The quintessential quantity for the star is basically its mass. If you would take two stars from different corners of the universe and they have the exact same mass and are equally old, they would appear identical. As it was evident from the previous metaphor of the magnetic spheres, it is quite difficult to bring the magnets or basically protons together. However, under the presence of a large pressure, it is in fact possible to bring the nuclear particles together. The core of a star is among the few places in the universe where conditions are sufficiently extreme for such a process to take place. However, depending on the age and the mass of the star, fusion can take place in different ways and also by using different starting elements, ending with formation of various different products. We classify these stars and put them up on a chart called the Hertzsprung-Russell diagram. Most stars are actually quite small, slightly smaller than the sun, which itself is not so large as compared to the largest observed stars. All low mass stars early in life fuse hydrogen to form helium. Most of these stars in the universe are red dwarfs. These stars are so small that after they burn hydrogen, they start cooling down and immediately become white dwarfs without a helium burning phase. These are called helium white dwarfs. However, the waves in which hydrogen is burnt can vary when the mass of the star is increased. In uh, in all relatively small stars, the hydrogen gets converted into helium via the proton-proton chain reaction. It is the most rudimentary and common form of fusion, and it doesn't require any catalyst to take place. Now, before we move ahead with discussing this proton-proton chain reaction, I would like to take a slight detour to explain to you the particles that are found in nature. So, this is basically the standard model of particle physics, and it is our best guess at the fundamental building blocks of nature. Now, the whole table is not actually relevant for this discussion, but I especially wanted to highlight over here the neutrino. So, it is a fundamental subatomic particle that is incredibly abundant in the universe, but it's very, very, very difficult to detect because they actually rarely interact with normal matter, and hence they have the term named like as ghost particles. To put this into perspective, trillions and trillions of neutrinos are passing through your body right now, but you cannot notice them as they go completely unnoticed and they don't interact with your body. They have no electric charge and have very little mass and also interact only through the weak nuclear force and the gravitational force. Now, let me come back to the proton proton chain reaction process. So, the process is actually quite simple. We, there are two hydrogen atoms fusing to form a helium 2 nucleus, which is basically just two protons combined together. However, because there are no neutrons, this state is actually highly unstable. Therefore, this isotope emits an anti electron, also called as a positron, and an electron neutrino is also emitted. Finally, a deuterium nucleus is formed. So, here in the diagram, we can see that there's this gray sphere and this red ball. So this is actually the deuterium nucleus. So, but what is this positron that we saw from before? That this white particle. So positron is basically like the evil twin or the antimatter counterpart of the electron. Fuses with another proton to form this is it. Fuses with another proton to form a helium 3 nucleus while a gamma ray is released. Gamma rays are the most powerful form of electromagnetic radiation, way more powerful than visible light. Two of these helium 3 nuclei will fuse to spit out an alpha particle or a helium 4 nucleus and also two protons. This last step is the most energetic process. However, all these reactions generally give off gamma rays, not heat, light, or UV. However, if you notice, uh, the energy that we get from the sun is mostly in the form of visible light, heat, and UV rays. So, where did these gamma rays go? So, actually, what happens is when the gamma ray is traveling from the core of the sun, where it is produced, outwards to the surface of the sun to exit and reach us uh, through the atmosphere, what happens is it gets absorbed and re-emitted and absorbed and re-emitted and so on and so forth millions of times before it can even exit the star. So what this does is it steals most of the energy that the gamma ray harbors. So what this does is that it converts the gamma ray into either UV light or normal light, visible light, that is, and infrared light, and all these kinds of different wavelengths, which have much lower energy. So this is how the proton-proton uh, chain reaction works. Now I will move on to explaining in larger stars the cycle known as CNO cycle. So this is a cycle where instead of fusing hydrogen directly to form helium, there are multiple catalysts which help in the reaction. So this is how the reaction takes place. A proton fuses with carbon nucleus to form a nitrogen 13 nucleus. Then this then undergoes a decay and forms a carbon 13 atom with the release of an anti-electron or a positron. Then this carbon 13 atom with the release of uh, another anti-electron will give the nitrogen 14 isotope. Uh, the nitrogen 14 will absorb a proton to release yet another gamma ray and form an oxygen 15 atom. This oxygen 15 undergoes beta decay to form a nitrogen 15 atom. This then captures another proton and splits into a carbon 12 atom and helium nucleus, starting the whole cycle again. Stars undergo this type of fusion only in later stages of their lives, since only during these later stages do they actually have the abundant amounts of carbon, nitrogen, and oxygen to carry out the reactions. This phase occurs in stars slightly larger than the Sun, where the core is completely or almost completely exhausted of hydrogen, but the area around the core has hydrogen and carbon. This process takes place in the shell around the core, while at the same time the core itself is burning helium. So now I would like to move on to another uh, fusion process that occurs in stars called the triple alpha process. So it mostly happens in these huge stars that we can see in this range of the Hertzsprung-Russell diagram. So supergiants, bright giants, and giants. So this range is basically where this happens. So the triple alpha process is a set of nuclear fusion reactions by which three helium-4 nuclei, also known as alpha particles, are transformed into carbon 12. The process is the primary mechanism for the creation of carbon in the universe and is fundamentally responsible for the existence of carbon-based life. During the main sequence of a star's life, like our sun, it fuses hydrogen into helium in its core. Eventually, the hydrogen fuel is exhausted. Without the outward radiation pressure from the hydrogen fusion, gravity takes over, compresses the core. This compression causes the core's temperature and density to skyrocket. When the core temperature reaches approximately 100 million Kelvin and the density hits about 1 lakh gram per cubic centimeter, the helium nuclei have enough energy to overcome their the electrostatic repulsion that is present between them. At this point is when the helium fusion begins. So two helium-4 nuclei, as you can see here, uh, fuse to form a beryllium-8 nucleus. This reaction is actually endothermic, as in it absorbs a small amount of energy rather than releasing any. Now, the beryllium-8 is actually extremely unstable. It has a half-life of roughly 1 in 110 quadrillion seconds, means meaning it decays almost instantly back into two alpha particles. However, because the core is so incredibly dense and hot, helium nuclei are constantly colliding. This creates a tiny but steady concentration of beryllium 8 in the star's core. Before the beryllium 8 nucleus has the chance to decay, a third helium 4 nucleus fuses with it to create a stable carbon 12 uh, nucleus. This reaction releases the high energy gamma rays that we know. The overall reaction, as we have seen, is basically the conversion of three alpha particles into carbon 12 nucleus. The defining feature of this reaction is basically how mathematically lucky it is. So, based on the collision probabilities, this second step, as in the uh, helium 4 combining with the beryllium 8, is astronomically small. So, in 1952, however, astronomer Fred Hoyle realized that for this process to work efficiently, there had to be a specific nuclear resonance or nuclear state of sorts. The combined energy of the beryllium 8 nucleus and the incoming alpha particle had to closely match a specific, undiscovered excited energy state of the carbon 12 nucleus. Hoyle predicted that this carbon 12 must have an excited state at approximately 7 electron volts above its ground state. Nuclear physicists conducted experiments shortly after and found that this exact state actually did exist. This state is now known as the Hoyle state. When beryllium 8 and helium 4 fuse, they form carbon 12 in the excited Hoyle state. While it often decays back into its constituents about 1 in 2421 times, it actually successfully emits a gamma ray photon and drops to the stable ground state of carbon 12.
Well, there are obviously going to be way more ways in which fusion can take place, but these three were the most important ones. There are, of course, going to be advanced burning stages as well, where more different types of fuel and heavier elements get fused into even more heavier and heavier elements. But there's no point in looking at all of them in detail. But before we move on to the advanced burning stages, let us take a moment to look at the energy output of the various forms of the basic fusion. Now, there is, of course, the PP chain, the CMO cycle, and the triple alpha process. This particular graph represents how these processes have energy output and at what temperature these take place. So, this is a plot of the log of the energy and log of the temperature. Now, as you can see, the PP process does not give off a large amount of energy and it also takes place at a much lower temperature. This is quite understandable because most of the smaller stars, the sun included, undergo this particular process of fusion. Now, we need to understand this. The sun is actually larger than around 85% of all the stars known to us. But then, most of these stars are red dwarfs. And all these stars, they perform fusion at a very slow pace. They are like small candles, but they burn so slowly and so dimly that we cannot even see them in the night sky easily, at least not without a telescope. And the same holds true for a lot of small stars. They burn slowly and steadily for billions of years. Actually, red dwarfs are predicted to have lifespans of even up to 10 trillion years. For context, the universe is only about 14-15 billion years old. However, there are outliers as well. These outliers are usually on a different part of the Hertzsprung-Russell diagram. Now, when you think about it, there are obviously going to be a rare few stars which are extremely massive, and they are also going to have a short lifespan, and therefore we won't really be seeing much of them 10, 12 billion years down the line. But right now, the universe is still relatively young, so we can observe a lot of them as of today. So these large stars generally have a much shorter lifespan and they burn all their hydrogen in a few 100 million years or so. For context, the sun will burn hydrogen for a total of 10 billion years. We're already down by 5 billion years. So there's 5 billion years remaining until which the sun can burn hydrogen. These stars, on the other hand, rush through it in a few 100 million years, and then they burn through the helium in a few tens of millions of years or just a few million years. But then they also do this very fast, and therefore they end up at the advanced burning stages of their life. That is to say, they start burning elements like carbon, neon, oxygen, and silicon. And other elements are also present, but these are the main important ones. So these stars which you see on this part of the Hertzsprung-Russell diagram are called supergiants. They're usually blue and yellow. There are also red supergiants, but they are also outliers, but they are outliers amongst the outliers. So let's just look at the blue supergiants for now. So these supergiants have multiple layers or shells. There will be a hydrogen burning shell, there will be a helium burning shell, carbon burning shell, neon burning shell, oxygen burning shell, and a silicon burning shell. Now, all of these are taking place at pretty much the same time. But however, let us take a moment to appreciate how short lived these stars are. Compared against the red dwarfs, which can go for 10 trillion years, or even the sun, which can even go for 10 billion years, which is a large period of time, these stars generally have the lifespan of only a few hundred million years. And then at this particular stage of their life, they have very little time left. Because once all the helium is burned out, the carbon starts to burn. And this phase takes about 600 years in large stars. And then comes the neon burning. This takes 10 years. However, as we go on further to oxygen burning, we will be done in about 6 months. And then silicon will be burned in about 1 to 5 days. But here we hit something. Remember how I said that there is something called the binding energy per nucleon? And it turns out that iron has the highest binding energy per nucleon, which makes it the most stable nucleus. It kind of poses an issue here because pretty much any element up and until now could be burned. But then silicon has a mass of 28, which means if you combine two silicon atoms together, you get an iron 56 atom. And this is where we reach a dead end because if you want to further react with iron, you will end up putting more energy into the fusion process than you're gaining out of it. And similarly, if you want to enable fission in iron and get smaller products, that is also not possible because iron is the most stable element. So you will still end up losing more energy than gaining. So what happens here is quite catastrophic to say the least. What happens here is that the star collapses because effectively a star is just a giant tug of war of sorts. On the one side, there is gravity trying to crush the star inward, and on the other side, there is the fusion reactions taking place inside the core of the star. And the fusion reactions will end up emitting a lot of energy, and this energy builds up a sort of internal pressure, if you will. And this internal pressure is what prevents the gravity from collapsing the star. But however, once the core becomes completely made of iron, no more nuclear reactions can take place. And this is where the star will collapse. And that is as much as stars are concerned. And frankly speaking, stars don't burn in the literal sense, they violently fuse the nuclei. And that is as far as natural fusion is concerned. Now, let us look at the artificial or man made ways in which nuclear reactions take place and how it is beneficial to us or not beneficial as well. Now, before we move on to looking at the various ways in which we perform nuclear reactions, we need to understand this. Fission itself was initially considered to be an impossible task because at the time when it was hypothesized, people did not know about the existence of the neutron. And that is why it was thought that there wouldn't be a sort of chain reaction process taking place, which is necessary for fission. But later on, with the discovery of the neutron, this was proved to be possible. And yes, that is true. But before we look at the actual mechanism behind what is happening, we need to look at a few things which were observed. Scientists performed fission experiments and they would look at the mass of what was present originally in the form of the fuel and the mass of the byproducts which were received. The mass of the byproducts was actually lesser than the mass of the fuel. But this doesn't make sense. Of course, the discrepancy in mass is very small. If you put 1,000 grams of fuel, maybe you would lose like 0.1 gram or something like that. These are not actual numbers, these are just ballpark figures. But nonetheless, these mass differences were not actually negligible. To understand what exactly is going on, let us go and talk to history's most famous patent clerk. Now, some of you may recognize this dashing young man here as none other than Albert Einstein. Now, what exactly we need to understand from this conversation here with Einstein is this: mass and energy are interconvertible. Now, To understand the exact nature of this and the relationship between mass and energy, we will look at history's most famous equation. E is equal to mc square. You may have seen this equation before, but this is what it means. Mass itself need not necessarily be conserved, as how chemistry people would think earlier. But rather, mass can be converted into energy, and if you have the right equipment, you can convert energy into mass. But then there is a mathematical relationship defining on how exactly this can take place. So, this particular equation is going to state as follows. On LHS, we have E, the overall energy outputted. On the RHS, we have M into C square. M is the overall mass which will get completely destroyed, not burnt, not dissolved, not melted with acid, not powdered, but completely gone. If you take a weighing scale and measure what is there, the mass is just not present. And in such a case, E will be equal to mc square. That is, upon the destruction of said mass, the overall amount of energy which is outputted is m into c, where c is the speed of light. This equation is quite important because it shows us how truly energetic the destruction of mass and matter really is. Because c itself is 3 followed by 8 zeros or 300 million. C square is 9 followed by 16 zeros when you are measuring in meter per second, or rather meter square per second square. So what this means is that even if you put in a small amount of mass, a very tiny amount of mass in fact, we will have a large amount of energy coming out the other end. For context, if you were to take 1 gram of matter and you are able to completely destroy it, you would get 9 into 10 power 13 joules. That is to say, 90 trillion joules. For context, let us take the example of normal household appliance. For example, an LED bulb. Now, LED bulbs generally take 10 watts of power, which means if you destroy just 1 gram of matter completely, you'll be able to power one LED bulb for 2.5 billion hours. That is how much energy is truly emitted. Now, what these scientists were observing was that some amount of mass would be gone because of the nuclear reactions, but that is what they observed as energy as the output. That is to say, the sample would heat up or it would give out a large amount of gamma or X rays or even light in certain cases. So that is where all the missing mass went. And this missing mass is called as the mass defect. Now, let us look at how nuclear reactions actually take place. So, if you look at the diagram here, you will see some sort of a chain reaction going on. And to understand this, let us look at the analogy of the marbles made of magnets and wood again. Suppose you have a very large clump, much larger than iron, so large in fact that the super glue cannot hold everything together. The super glue is actually falling apart, and any small amount of energy supplied will genuinely destroy the nucleus. So, in such a case, we have the example of uranium 235 here. So, what happens here is that assume for a second that, say, a scientist fires a single neutron in one of these uranium 235 atoms. What happens is that the uranium 235 atom absorbs this neutron for a second, but only for this one instant. It's not even a second actually. It will be along the lines of a few nanoseconds or a few picoseconds. That is to say, about a quadrillionth of a second, maybe. So, at this particular instant, this uranium nucleus becomes highly unstable and it breaks apart. And the issue here is that the superglue is very weak at this particular point of time, and the magnetic forces have overcome the superglue. But now there's so much magnetic repulsive energy stored in between there because of how closely these magnets are clumped together that everything comes flying apart at very high speeds. And that is also what happens in the case of nuclear fission. Lots of these particles just explode outward in all directions. And with these come some other neutrons. Now, these neutrons, they can be absorbed by some neutron absorbing material, or they can collide with some more uranium atoms, which in turn will go and start more fission reactions as we speak. So that chain reaction is what is necessary in either nuclear reactors or even in nuclear bombs. Which brings us to a question: how likely is this to actually take place? Now, think about it. If I have a thin sheet of uranium and I hit a very thin stream of neutrons and I ensure that fission takes place at one corner of the uranium, nothing much will actually happen. There will be maybe a small flash of light, and everyone in the room will die horrifying deaths. But nonetheless, there won't be a grand explosion of sorts, nor will there be a nuclear reaction of sustained power, that is to say. But nonetheless, we do have nuclear reactors running, and we do have nuclear bombs as well. So the question is how? Again, the answer is straightforward. Instead of having a sheet where neutrons can emerge in all sorts of random directions, what we do is we clump a lot of pure, fissile, unstable uranium atoms in a small space, and we give it a steady supply of neutrons for a few seconds, and then the rest of it is just continued by the chain reactions which were initiated. So, for these chain reactions to be sustained for large durations of time, you need a certain threshold mass. And this threshold mass, a critical mass, is scientifically called, well, if you guess it, it's critical mass. And this is what is the minimum mass necessary for sustained nuclear reactions to take place. The following image shows something called the demon core. Now, scientists are generally bad at naming things, but this one, it really earned its name. This particular object has killed multiple scientists who are experimenting with it because when trying to figure out where exactly a core can go critical, a core of nuclear fuel can go critical, scientists, well, they ran into certain accidents and there were radiation poisoning incidents, which is what gave this particular object its name. This was actually supposed to be part of a third bomb from the Manhattan Project, but since the bomb never really fell, scientists had this to play around with, and unfortunately, they paid the price. So, the takeaway from this particular section is that to sustain fission, you need to have enough fuel and you have to reach the critical mass. But then, this might raise a question: what if we have enough of this fuel, but it occurs naturally? What if nature can build its own nuclear reactor without humans? Well, the answer is that it is not just possible, but it already has happened in the past. This brings us to what is called as the Oclo reactor. So, nature has beaten us to fission, yes, that is true, and sustained fission for that matter. And this Oclo reactor is currently in Africa, right? But nonetheless, truth is, nature had something going on for a very long period of time as well, and much longer than anything which we have built. So the Oclo reactor, if you look at the image here, is basically looking a lot less like a machine and more like rock formations. Well, here you can see the reactor sites. They're labeled as one here, those dark patches on the uh, white strip of land. The patches marked as 1 were the actual reactor sites. The large white strip marked as 3 is the uranium ore, which hadn't reacted. 2 represents the sandstone, and 4 is granite. But that is the overall uh, composition of the Earth in that particular region. So, what happened here 2 billion years ago is quite surprising actually. There was a lot of uranium rich material, and at one point of time, water started seeping there. Now, this is quite important because without water, nuclear reactions wouldn't have been possible because water acts as a moderator. It slows down neutrons. This is necessary to keep a nuclear reaction going on for long periods of time. So, this particular nuclear reactor ran for anywhere between 1 lakh to 3 lakh years. That is much longer than any machine which we have built. And when you think about it, it is quite elegant actually. And more importantly, this raises quite a lot of questions and a lot of interest is there in the scientific community towards this as well. Because there has been no significant radiation poisoning as such or any sort of pollution, contamination, anything. So this has enabled scientists to think of well solutions and potential ideas for disposing of nuclear waste without having it contaminate the environment to a large extent. And another thing which is important about this is that for these reactions to occur, you require water with a small amount of oxygen in it because this can help in dissolving of uranium, which has happened in these particular regions. Now, the reason why this is important is because 2 billion years ago, we didn't really have plants to photosynthesize and we didn't really have oxygen on the earth in the way which we have it today. Our atmosphere was more rich in carbon dioxide actually. But the evidence here says otherwise. So there have been specimens of fossilized bacteria found on the walls of caves near this region, which has led us to speculate that maybe these bacteria could perform photosynthesis, which is what gave oxygen for these reactions to occur. Now, that is as far as natural reactors are concerned. Now, let us look at the more practical engineering applications of it. Let us look at man made nuclear reactors. Now, if you look at this,
Yeah. So, as it was mentioned, the radioactive elements spit out many number of particles, right? We have seen this. Now, another thing is they obviously also spit out energy, and gamma rays that we have seen before is also a form of energy. So, being smart, what did smart people do? They used it to boil water, of all things. Then the water obviously becomes steam and it spins a turbine, which actually produces the electricity. Now, to have this working, we need quite a bit of a setup. Unlike natural radioactive decay, where elements spontaneously spit out particles, commercial reactors rely on induced fusion. A heavy, unstable isotope, typically uranium 235, is bombarded with a free neutron. The nucleus absorbs this neutron and briefly becomes the unstable uranium 236 isotope. This nucleus splits into two lighter elements, which is the fission fragments, releasing 2 to 3 additional free neutrons and a massive amount of energy. The energy released is due to the mass defect that we saw earlier. Basically, the resulting fragments, if you take their masses and add them up, the total mass will be lesser than the original parent nucleus's mass. So, where did the little bit of extra mass go? That actually goes into the energy. So, that's what we saw from before as well. Equals mc square. So, the little bit of mass that is lost is converted into energy using that equation. So, most of the energy actually manifests as kinetic energy of the fission fragments, which collide with surrounding atoms, generating an intense amount of heat. To harness this heat is the main goal. So, how do we do this without causing a huge uncontrolled explosion or a meltdown? So, some specific architecture is required for this. That is, some specific engineering is done for this. So, let's look at the structure of the fission reactor. So, first we have the fuel rods over here. So, these are basically long tubes filled with pellets of enriched uranium oxide. Then we have the moderator. So, why do we need this moderator? Basically, there are fast moving neutrons produced by the fission process that are unlikely to trigger further fission. So, a moderator, like usually ordinary water or something that we call as heavy water. So, what is this heavy water? It's basically uh, normal water where the H2 in H2O is replaced with D, as in deuterium, which is an isotope of hydrogen. So, this liquid helps us to slow down the fast moving neutrons. Then we have the control rods over here, which is made of neutron absorbing materials like boron, silver, or cadmium. Inserting them into the core absorbs neutrons and slows the reaction, while withdrawing them does the opposite and actually accelerates them. Then we also obviously have the cooling system that is present in the reactor. Usually, a fluid is used like water, obviously, but sometimes we also use gases, and this circulates through the core and absorbs the intense amount of heat. Then we have the pressurized water reactor. Basically, it's just a part of the nuclear reactor. That is, the extremely hot, highly pressurized primary coolant water passes through a heat exchanger, transferring its thermal energy to a secondary lower pressure water system or water loop. This secondary water boils into steam, which is forced through a turbine linked to an electrical generator. So, this is what actually produces the electricity that would power our homes. Now, all this is very nice. I want to take a slight detour over here and show you some really cool phenomena that we can see in these uh, fission reactors. So, this first is the world's first nuclear reactor. So, with all our sophisticated technology, obviously, we just end up boiling water, and that's quite ironic, I would say. So, I would like to now talk about Cherenkov radiation, and the title might surprise you. When you travel faster than light, how is that possible? So, let me explain. But before that, let me actually show you this beautiful phenomena of Cherenkov radiation. So that was absolutely mesmerizing, at least for me. That brilliant blue color is just treat to watch. So let's actually explore what is happening over here. So the easiest way to understand the Cherenkov radiation is to think about a sonic boom. When an airplane flies through the air, it pushes sound waves out ahead of it. But if the pilot accelerates and breaks the sound barrier, i.e., he basically flies faster than the speed of sound itself, those waves actually cannot get out of the plane's way fast enough. So they basically compress and pile up behind the jet, creating a massive shock wave that we hear as a boom. This is basically a sonic boom. I'm sure we have heard about this. I personally have heard about a sonic boom happening over the city actually a few years back. So this is something that we are relatively familiar with. The Cherenkov radiation is actually the exact same phenomena, but instead of sound, it's light. Basically, it's a subatomic particle somehow outrunning light. So we are often taught that nothing can travel faster than the speed of light. But this statement has a caveat. Nothing can travel then nothing can travel faster than the speed of light in a vacuum. However, when light enters water, it slows down significantly. Much like how it's much harder to wade through water rather than just run through atmosphere. So, one interesting phenomena here is that actually the energetic particles that are released during nuclear reactions don't get as slowed down by the water as the light does. Therefore, a particle can enter a pool of water traveling faster than the speed of light. And uh, this is in relative to the light that's actually traveling in that water itself. So, when this happens, the particle breaks the light barrier, if you will, of that specific reactor. When this super fast particle moves through this water, it disrupts the atom that uh, are in front of it. These atoms get excited and try to release that sudden burst of energy as light. But because the particle is moving faster than the emitted light can travel, the light waves bunch up, much like they bunch up here in front of the aeroplane. So they constructively add up and form this cone shaped shock wave of light trailing behind the particle. That concentrated shock wave is nothing but the Cherenkov radiation. So as you could see, the result of this was that there was an eerie blue glow in that reactor. So when this optical shock wave is generated, it releases light across various colors. But why do we see only blue? So the reason is actually the process favors high energy waves. On the and we know on the visible light spectrum, red has the lowest energy, while blue and violet have comparatively higher energies. The process creates a massive amount of UV radiation and blue light, but virtually no amounts of red light or orange light or any of these. But obviously, as you know, we cannot directly see these UV rays as they're not perceivable to the human eye. So all we can perceive is the brilliant blue glow. Now, the actual phenomena of Cherenkov radiation is quite cool, agreed. But rather than it just being a cool side effect of nuclear reactors, it actually has real world applications. So one of these applications is basically catching these so-called ghost particles that I talked about before. If you remember, I was referring to the neutrinos. So as I said previously, that they are very very hard to detect, and it's because they don't react with anything. However, this there are reactors built where it's filled with ultra pure water lined with light sensors. When a neutrino rarely happens to crash into this water molecule, it knocks an electron away at faster than light speeds, as in faster than the speeds that light can travel in that specific water. This creates Cherenkov radiation in the form of a tiny blue flash. Now, while we can't detect neutrinos directly, we can definitely detect a small blue flash of light. So, this is what is done to detect these ghost particles. Now, what you see in front of you is actually a detector for one of these neutrinos. So, this is situated in Japan, and it's called the Super Kamiokande, and it is basically what I'd explained before, a huge tank, if you will, filled with ultra pure water. Now, there is another use of this Cherenkov radiation, as in sometimes instead of looking for stars high up in the night sky, maybe it's hard to observe them because of various factors like maybe it's obscured by some other object in front of the star or something like that. So instead of looking directly at the stars, some observatories look for flashes of Cherenkov radiation happening right here in Earth's atmosphere to track these high energy cosmic rays that hit our planet.
Well, that was quite enlightening, Rajiv. So, as Rajiv was very kind to point out, that all of our sophisticated technology goes towards, well, boiling water. We did come up with a different type of technology to harness nuclear power. I'm talking about the lesser known RTG, or radioisotope thermoelectric generator. Now, the name is quite complex, but frankly, the mechanism of how it works is quite simple. If you look at the schematic here for an RTG, it is quite simple. Basically, what you do is you take pellets of nuclear fuel, you put it in a capsule of sorts, and then you put something called as a thermocouple around it. So thermocouples are basically electronic objects or devices which absorb heat and give out electricity without any mechanical device of any sort. And therefore, this process is actually quite highly efficient. And more importantly, these nuclear reactions, they aren't in a chain of any sorts. It's not a self-sustained chain which can potentially cause an explosion or a meltdown or anything. But more importantly, it is more of a safe way to extract nuclear energy at its own pace. So the mass here is much lesser than the critical mass, but it is still sufficient to give out a small dosage of radiation and energy at all times. So these particular generators make for very long lasting batteries because, well, nuclear reactions can go on for lots and lots and lots of time. Because let us take the example of uranium again. Uranium 235 slowly decays, and half of it gets depleted every once in 4.5 billion years. That is the age of the Earth, actually. So once the Earth is twice as old as it is now, only half of what is there today will be gone. And again, it will go half and half and half, so on and so forth. So therefore, for our purposes, where the longest projects will be running for maybe 20, 30 years, these batteries are more than capable of giving us energy. So that is what these are. And therefore, the RTGs are used in space probes and in places like Arctic observatories or underwater exploratory observatories, which are unmanned, where humans just cannot access and replace batteries. The image that you see here is a small chunk of plutonium oxide, PU2O. So now what this is the fuel for an RTG. And the reason why it is glowing red is because it is quite hot from its own internal radiation. I mean, it's not irradiating, otherwise the camera would be dead and so would the photographer, and the camera wouldn't have been able to take a picture of this high quality. It would be highly grainy. But instead, what happened here is that it was wrapped in a neutron reflecting blanket of sorts, probably a graphite blanket, so that any neutrons which were emitted outward would go back in and cause some more reactions. So this would be sufficient enough to heat up the block for a small period of time, but not enough to cause an explosion or to keep a large sustained nuclear reaction for a long time. Now, let us move on to fusion reactors, perhaps the key to unlimited clean energy. Well, fusion is a lot more different than fission because for fission, you need nuclear fuel, which is firstly there, secondly, dangerous, thirdly, difficult to purify, and fourthly, it can be used to make weapons. So nobody really wants much of that floating anywhere because it's a risk in all sorts of ways, in the worst possible ways, actually. On the other hand, for fusion, the necessary materials are actually quite easily harvested, relatively easily harvested, and they're way more abundant. The raw materials for fusion to take place are various isotopes of hydrogen and helium, especially. So, how exactly we harness these is by taking, well, water and removing certain isotopes of hydrogen from the water molecules. Like initially, there is first something like deuterium oxide or heavy water, and very small amounts of tritium oxide, which is much heavier water. And then we can separate these out from normal water, and then via chemical processes we can turn it into nuclear fuel of sorts. So, how exactly fusion takes place is a lot more different from fission, because in fission, things are just breaking apart, they're falling apart. But for fusion, you need to push together things which like to stay apart. And atomic nuclei, due to their, well, positive charges, stay away from each other. However, for fusion to take place, we should definitely bring them close enough for the extremely strong superglue or strong nuclear interaction to take a hold and form a larger nucleus. So, how exactly we do this? Now, that's the real question. Now, the most common method is by using a device called as a tokamak. It's a Russian name, and basically, what we have here is that we will take the various gases, which are hydrogen and helium isotopes. We charge it up so much that the electrons are completely lost, and what we have is basically just an area filled with only protons or deuterium nuclei or alpha particles. And then what we do is that since these are charged particles, we can move them around with the help of electrical and magnetic fields. We use magnetic fields to spin these charges around in a circular area, and this is done in a donut shaped reactor or a toroid reactor. Toroid means donut shaped. And in this toroid reactor, we have these high frequency spinning objects, and high frequency because they complete the revolutions very fast, multiple thousands of times per second, or even millions of times. And these spinning gases, they are colliding with each other, or rather, the nuclei are colliding with each other, and fusion takes place. And then this in turn will eject a lot of neutrons, these processes. So if you look at the schematics of such a tokamak reactor, you'll see that it may look a bit complicated, but it's actually fairly straightforward. There is a plasma, there is something called a cryostat, there is the toroidal coil, there's the blanket. Now, these are the main points which you should really be paying attention to, because, well, the plasma is what is really the active ingredient, if you will, participating in the reaction. The cryostat is basically keeping the magnets cold, because these magnets will have to give off extremely powerful magnetic fields for this level of control. And these powerful magnets can only exist at near zero temperature. That is to say, these temperatures are the coldest in the universe, coldest thing which man has ever built. And these go to around minus 272 degrees Celsius, or nearly 0 Kelvin, like 1 or 2 Kelvin is the usual temperature. And once these magnets are cooled, they have the ability to generate a very strong magnetic field. And this is actually controlling a plasma, which in turn is hotter than the surface of the sun. Actually, much hotter than the surface of the sun. The surface of the sun is only around 6,000 degrees Celsius, but this can reach hundreds of thousands of degrees of Celsius, or even a billion degrees Celsius. So, on one side, we have the coldest object created by man, and on the other side, we have the hottest thing created by man. And this balance is a bit difficult to maintain actually, because the cooling itself takes up a lot of energy, and the energy required to maintain the magnetic fields is also quite large. So that is the reason why these reactors, though they keep improving, haven't yet created a fusion reaction where we have had more energy pulled out than the one which we had put in. However, there are alternative approaches to fusion. Another popular approach being something called laser confinement fusion. It's also called inertial confinement fusion. So now, if you look at this image, it is fairly straightforward. Instead of taking a plasma, accelerating and colliding it with a bit of plasma, what we have here is a small pellet of the given fuel, and then we blast it with lasers on all sides. And these lasers are powerful, which end up heating the pellet so much that fusion is possible. And also, the pressure with which it collapses inward is also sufficient to mimic the core of a star. So, these pellets are actually quite tiny. That is a reference of image where you can see the pellet on the tip of a human's finger. And these pellets are usually 2 millimeters across. Now, what exactly happens here, as you can see in this image, is that this pellet is placed in a canister of sorts made of reflective material. And there are multiple arrays of lasers or multiple clusters of lasers which all point towards the canister. Some of these lasers make direct contact with the pellet, some of them reflect from the canister and then make contact. But overall, the point is that they completely symmetrically hit the pellet. This in turn causes a fusion reaction. Now, there have been instances where this method has given out more energy than the lasers had put in. But nonetheless, this probably won't be economically feasible in the closed future because despite the fact that the lasers are putting less energy than what they received out, the amount of energy or electricity consumed to create the laser itself is much larger, and the creation of lasers is inefficient, at least at these scales. So that is the reason why, even though we can potentially use this, this method won't be economically viable for the foreseeable future. Now, let us look at the one big breakthrough which we have had in recent years. A company called Helion, based in Europe, has created a new reactor. This reactor is different from the tokamak reactors, which is using magnetic confinement, and the laser confinement reactors. So, here's what Helion has done. First, we get deuterium and helium isotopes to be heated until they form plasma. And then, using electric and magnetic fields, we accelerate the plasma. And on the other end of the reactor, we have another similar chunk of plasma. And once they're all accelerated towards each other, they compress and collide. This causes fusion. Now, this reaction ends up producing a lot of heat and energy. However, unlike in other reactors, we do not use boiling water. You see, the thing is that in laser confinement and magnetic confinement, we would have a blanket layer around the reactor, which in turn would absorb the heat and uniformly distribute it to a tank filled with water. So again, like cavemen, we end up just boiling water and then we harvest this energy by using a turbine. However, helium solution is much more elegant because they realize something. Since there are charged particles moving about, we can directly use this current to induce another current in an external circuit, which in turn can be stored as energy. And that is exactly what they have done. And this is a much more efficient process because we do not have any spinning turbines and other mechanical objects where energy is lost more easily. This particular image shows us the inside of one such reactor. A professor once told me the problem of sustained fusion for clean energy is not an issue with the physics, but rather of engineering. What he meant is that, well, nuclear reactions are exothermic, which means they really want to take place. We just can't get it done. But again, we can't really put two atoms together in the same area and expect them to fuse. No material can be used to crush it. You can't use a hydraulic press. What you need is a large electric field or a magnetic field to do the job for you. Because any object which is used will also end up getting destroyed in the process. So for sustained fusion, you need something like lasers or electric fields. And this in turn can be produced, but not very efficiently. So therefore, the problem lies not in the physics behind it, but rather in the engineering aspect of it. Now, let us move on to everybody's favorite topic, the fission bomb. Humans first created the fission bomb before we had a self-sustaining nuclear reactor for energy consumption purposes. And well, let us look at how it's really made. But first, let us talk to the father of the atomic bomb, J. Robert Oppenheimer. So the principle was fairly straightforward. Once it was discovered that fission is truly possible, every physicist in the world started thinking the same thing. If we trigger a chain reaction, we could create a very large explosion. And that is precisely what Oppenheimer did. Now, to understand how a nuclear weapon, to be specific, a fission bomb is made and how it works, let us go through the steps. Actually, I'll give you the steps of how to make a nuclear bomb. So, step one, get enough uranium ore in one place. All the best doing it and not getting caught by various governments. And step two, get rid of all the chemical impurities. Your uranium ore will often have sand in it. It will have various oxides of all different form of Earth's crust. It can have aluminium, it can have iron, etc., etc. You need to get rid of all of this via chemical separation processes or even physical processes. Right? What you'll be left with is some sort of oxide or some other compound of uranium. And this pure uranium is still not suitable for our purposes because what you'll have here is primarily going to be uranium 238. Now, uranium 238 is also unstable, but nonetheless, it doesn't really trigger a chain reaction in the same way uranium 235 does because even when it undergoes fission, it doesn't really spit out neutrons the same way uranium 235 can. So now we have uranium 238 and uranium 235. Now, more than 99% of it is uranium 238. So, the question is how do you take them apart? And that is where the next step comes in. First, you must convert all of this uranium into uranium hexafluoride gas. Then, grab industrial grade centrifuges, lots of them, and keep running them for multiple years actually. Keep running them for years and years and years and years until the centrifuge is able to separate out the uranium 235 and uranium 238. Now, why this expensive, time consuming, and energy consuming process, you may ask? The reason is simple. Uranium 235 and uranium 238 are isotopes of each other, which means chemically they are identical. They burn the same, they dissolve in acid the same, so therefore you just cannot extract each other from the other. However, their masses are slightly different. So, meaning if you put it in a centrifuge, it effectively acts as a mass filter, if you will allow me to call it that. And this allows us to extract uranium 235. Congratulations, you have uranium 235, pure uranium 235, let us just say. And now we convert this into a suitable compound which is in solid state. And then we have a large clump of uranium. However, this did not blow up in your face because this is not beyond a critical mass. But at the same time, when you think about it, if you have exactly the critical mass of uranium in one spot, it will immediately radiate away some energy. It will immediately undergo a little bit of fission, but it won't really well, sustain itself because one moment it is above critical mass, the next it isn't. And also, this is quite dangerous because then as soon as you've produced the uranium ore, it's gone. It's just not there anymore. But nonetheless, it is possible to have nuclear bombs. In the case of nuclear reactors, we saw that despite having critical mass of uranium, it still didn't explode because of things like the control rod. But here, you need it to explode, but only at the right moment. So, how would you do that? And the answer to this is also quite straightforward. Take the uranium, make it into a ball. And remember, don't have a critical mass, have a subcritical mass, meaning something slightly smaller than the critical mass. Make a ball, cut it in half, make a small hollow in its center, keep a small explosive in there, which is connected to other explosives on the outside of the uranium core. And on the outside of the uranium core, have explosives start spherically symmetrically. That is to say, have it in like a sort of a shell, and all of them are supposed to be identical. When you press a button, the inner bomb, also known as the urchin, should explode at the same time as the outer bombs. So what this does is that it simultaneously creates a lot of external pressure and it heats up the inside of the uranium. So now the uranium atoms will have enough kinetic energy and under a sufficient amount of pressure upon the release of one or the other neutron from some randomly decaying atom, a chain reaction will be triggered because now the mass is not subcritical or critical. It is supercritical. Now, the same concept works for plutonium, which was used in the first nuclear bomb ever made, but nonetheless, we usually use uranium. So, what happens is that once it goes supercritical, it creates a domino effect. The first reaction is like a small domino. The second reaction is like a phone sized domino. The third reaction, a bit larger, maybe the size of a book. Then think about it. You can keep on stacking dominoes even to the sizes of buildings. Similarly, one reaction will trigger two, which in turn will trigger four, which in turn will trigger eight. And this keeps on piling up more and more and more until all the fuel is used up and so much energy has been outputted in such a small fraction of a second that it all completely blows up. And this causes an explosion. Congratulations, you're now on a watch list. And this is what the creator of the first atomic bomb said. I have become death, the destroyer of worlds.
Okay, let's now talk about the fusion bomb. A fusion bomb, more commonly known as a thermonuclear weapon or a hydrogen bomb, it represents basically the most destructive class of nuclear weapons which we have ever developed as mankind. While the earlier atomic bombs relied exclusively on nuclear fission, that is, the splitting of atoms, the thermonuclear weapons, that is, the fusion bomb, derives a significant portion of its explosive yield from nuclear fusion, that is, the combining of light atomic nuclei. However, initiating nuclear fusion requires conditions similar to those found in the core of a star, with temperatures exceeding 10 to the power 8 Kelvin. And along with this, we need immense amounts of pressure. To achieve this on Earth, a thermonuclear bomb uses a staged design, as in there are many stages to the bomb, where a standard fission bomb is used merely. Just a second, sorry. The primary fuel of the thermonuclear weapon is not some heavy uranium or plutonium, but rather isotopes of hydrogen. And these isotopes are basically uh, deuterium and tritium. So, when subjected to immense amount of heat and pressure, these isotopes fuse to form a helium nucleus and a free, highly energetic fast neutron. And basically, for this to happen, we actually need cryogenic level of liquid hydrogen in the bomb. But it is practically impossible to handle this kind of uh, material inside the bomb. So we use the solid chemical compound as a substitute, that is the lithium deuteride, basically a compound that's made of lithium and deuterium, which is an isotope of hydrogen. When exposed to neutrons during the explosion, the lithium breeds tritium, or basically generates tritium on the spot, which then immediately fuses with the deuterium. The foundational architecture of the modern thermonuclear weapons was developed by physicists Edward Teller and Stanislaw Ulam. That's why this design of the fusion bomb that we uh, most notably know is the Teller Ulam design. And it solved the problem of how to compress the fuel uh, before the initial fission explosion blew the entire device apart. The design physically separates the bomb into two stages within a reflective casing. The primary stage, which is basically a spherical i- implosion type fission bomb. It's similar to the bomb that was dropped on Nagasaki. Then there's a secondary stage, which is a cylinder containing the thermonuclear fuel of lithium deuteride that we discussed. And down the center of the cylinder runs a rod of fissile material. Basically, it could be plutonium or highly enriched uranium. This is basically known as the spark plug. The outside of the cylinder is wrapped in a heavy metal uh, tamper, basically, if you will, basically a casing, uh, which is made of uranium 238. Then there is the interstage. A plastic foam fills the empty space between the primary and secondary stages and the outer casing as well. The critical breakthrough of the Teller Ulam design is the radiation implosion. It uses the speed of light to beat the speed of sound. The entire detonation process of thermonuclear weapon, that is this bomb, occurs in a fraction of a microsecond. So I will now go through the sequence of how these phases occur and how the fusion bomb works. So the first phase, the fission, basically the fission trigger. So conventional high explosives detonate, uh, compressing the primary stage's plutonium core until it goes to a prompt critical stage. A runaway fission chain reaction occurs, releasing a massive amount of energy. Then the second stage, which is radiation implosion. So basically, the primary explosion releases roughly 80% of its energy, not as a physical shock wave, but rather as a brilliant flash of X rays. And because X rays obviously travel at the speed of light, they race ahead of the expanding physical debris of the primary stage. These X rays flood the inside of the bomb casing and are absorbed by the plastic foam filling that interstage. The foam instantaneously turns into an ultra dense, superheated plasma. Then the third phase comes, compressing the secondary uh, kind of uh, phase. The intense thermal radiation from this plasma that was generated, combined with the vaporization and the outward expansion of the materials, uh, specifically of the secondary stages outer casing, exerts an immense or incomprehensible amount of inward pressure on the cylindrical secondary stage that we talked about. This violently compresses the lithium deuteride fuel uh, and the central spark plug. Then the phase 4 occurs. The spark plug ignites. So basically, as the secondary stage is crushed inward, the plutonium spark plug is in the center of this compressed supercritical state. It undergoes its own fission chain reaction, and then now the lithium deuteride is trapped between the inward pressure of the radiation implosion and the outward pressure of the fissioning spark plug. Then the phenomena of thermonuclear ignition occurs. So basically, under this astronomical amount of heat and pressure, the fusion finally begins. So neutrons from the spark plug strike the lithium 6 and convert them to tritium and helium, and deuterium is also generated. So the tritium and deuterium fuse, releasing an immense amount of energy uh, of, and this is comprised of fast moving neutrons. And these neutrons are so energetic that they each contain around 14.1 mega electron volts of energy. So we come to the last phase of this bomb, which is the fission, fusion, and again fission cycle. So the fast moving neutrons released by the process are so energetic that they can induce fission in this outer secondary casing that we talked about, which is made of the depleted uranium 238. And in many of these bombs, this final fusion induced fission of the heavy outer casing accounts for more than half of the weapon's total explosive yield, and is a primary source for the weapon's radioactive signature or radioactive fallout. So basically, this fission cycle keeps going on and just uh, creates such an immense amount of energy that the bomb is so powerful that it could wipe out entire civilizations. It is really incredible to even see such levels of engineering which would turn our planet to dust in a matter of a few days or something. So, we now have the capacity to destroy large cities with the push of a button with this fusion bomb. So, thank you guys for this, for attending our session. We will now be taking doubts, and also in a few minutes we'll show the attendance QR so you can take your attendance. So, you have any doubts, put it in the YouTube chat. I'll either orally answer it here or maybe reply in the chat itself. Any doubts, you can put it in chat. I'll just show the QR in a minute.
I think everyone was scanned.
Just give them a minute. We'll wait for just one more minute. And any questions are there, you can feel free to put them in the chat or on the main summer school Horizon group. So we can have a nice kind of discussion if you guys want. Thank you guys for coming. We will now end the session. Hope you enjoyed this. Uh, eh, we can have a nice discussion on this topic if you want on the main Horizon group. Thank you. Macha. Yo.